I'm Edwin Huang. I'm a postdoc at EIUC. I'm going to be giving this talk on behalf of Tom, although both of us ended up not being here on Friday. And I'm going to be talking about quantum Monte Carlo studies of transport in the Hubbard model. This was work done primarily by myself for the first part while I was a student in Tom.
Sorry to interrupt, but could you turn down the volume of your microphone just a little bit?
Okay.
It looks like you're saturating the mic.
Where do I? Audio. Okay, is this better?
Yes.
Yes, much better. Thank you.
Okay. So this talk has two parts. The first part was while I was a student in Tom's group at Stanford, about strange metallicity in the doped Hubbard model. And then the second part is concerning DC Hall measurements in the Hubbard model. This is work carried out by Huang, who was with us at the conference for the first few days, and by Catherine Ding, who are both graduate students with Tom at Stanford. Okay, so let's get into it. My talk is also a continuation of the last two talks, so I really don't need to introduce this topic of strange metallicity. Let me just flash a few things to quickly to raise some motivating questions for the topics that I'm going to be discussing. So as Wasim already mentioned, in correlated materials, and for instance in cuprates, let me use this laser pointer thing. There is a strange metal regime where the resistivity is large as you increase temperature, violating the Mott-Yaffe Rego limit, and it is linear in temperature. And together, these two phenomena are incompatible with conventional Fermi liquid theory based on quasi-particles. So the question then is, what is the nature of the charge carriers? Is there still a quasi-particle description, or is there simply no quasi-particle description at all? And later, in the last part of the talk, I'll address the related question, related but not identical questions of, is there a Fermi surface in the Hubbard model? And what does the Hall coefficient mean? Okay, so since these topics have been introduced in the last two talks, I will simply just go into our calculations and present our results and discuss them. So this is about the Hubbard model, of course. We've seen this Hamiltonian many times throughout this conference. The method we're going to be using is determinantal quantum Monte Carlo. We use a typical parameter set of T prime over T of minus 0.25, U over T of 6, so intermediate interaction strengths. In the Monte Carlo, we consider cluster sizes of 8 by 8, and larger clusters will be shown to check for finite size effects. We go up to 30% Ho doping and check intervals of 5% doping from half filling to 30% Ho doping. And the lowest temperature we can reach is on the order of is equal to the hopping divided by 5, which is roughly an order of magnitude below the Fermi energy. For any experimentalists who are curious about what this means in units of Kelvin, if we use units comparable to the cuprate bandwidth, T over 5 corresponds to something like 700 or 800 Kelvin. So the temperature regime that we're reaching here is slightly overlapping with what's been done experimentally, where linear resistivity has been observed up to around 1000 Kelvin. Above that, of course, in the actual materials, the material starts to decompose or melt. But here, since we're just having a pure Hubbard model without any lattice that changes with temperature, we can access arbitrarily high temperatures. Now, these are calculations done using the very old method of determinantal quantum Monte Carlo, which is good because it provides exact results without approximations other than finite size effects. The disadvantage is that it has a fermion sign problem when you dope it, or when you have anything that breaks particle symmetry, such as the T prime term that we have. In this case, at our lowest temperature, the average fermion sign is on the order of 1%. And to really, there's no way around this in these calculations other than to use brute force. So what we do in these calculations are very high statistics sampling. So each parameter that we consider, each temperature, each doping, we use 500 independent Markov chains, each with 2 million measurements of the unequal time current correlation function. And just as a final note, this is simply the Hubbard model. The only way momentum can relax is through umlaut scattering, since there are no phonons and we have no disorder in a periodic cluster. Okay, so we are doing quantum Monte Carlo calculations of the current correlation function. And what we want to obtain is the optical conductivity. So there is no perfect procedure to do this, but one standard procedure is to do analytic continuation numerically using the maximum entropy method. To quickly outline this method, the idea is that we start with measurement in imaginary time of the current correlation function on the left-hand side, and this relates via an integral equation to the optical conductivity, which is what we want to obtain. The difficulty is that this is a numerically ill-posed problem. You can have variations here that, due to this integral, do not show up here. In other words, if you have error bars, which we always do due to stochastic sampling, there would be some errors that are unknown here. The procedure of maximum entropy is to maximize this functional, where you propose different spectra for the optical conductivity, and then you try to maximize this function, which has two terms. One is an entropy term, and one is a chi-squared term that parameterizes the deviation from the data. So what you're trying to do here is you're trying to fit the data as well as possible, but without increasing the entropy too much. And what this entropy essentially means is it's a measure of how much more information is in the proposed optical conductivity compared to a model function. So by balancing these two terms, what you achieve is a good fit to the data up to roughly the size of the error bars of the data without overfitting and introducing too many spurious features. For the experts in the audience, the model function that we are using here is an annealing method, which means that for each temperature, we're taking as the model function the next highest temperature. And at the highest temperature, we use a model function that is calculated based on a moments expansion. So let me first present the data, and then I'll discuss some of the limitations and our checks for how well this maximum entropy method works. But first, let me show some data so that we can roughly see what we're dealing with. So here is data for the optical conductivity obtained by Monte Carlo calculations, analytically continued via maximum entropy. This is the optical conductivity in units of E squared, the electron charge, divided by h bar as a function of frequency divided in units of the hopping T. And these different curves are different temperatures. The red curves are the hottest temperatures, the blue curves are the lowest temperatures. And we can see that as you decrease temperature, going from red, these dashed red lines, to solid red lines, to the solid blue lines, there is a gap opening, and this is at half filling, so this agrees with our expectations that we should get a Mott gap. So the presence of Mott insulating physics here confirms that, okay, we're in a parameter regime which has an intermediate interaction strength of 6, but this is still relevant to strongly correlated physics. Okay, let's see what happens now if we dope the model. So this is at 10% whole doping, and this is at 20% whole doping, with the colors representing the same temperatures. In all cases, all temperatures and both dopings, what we see is a Drude-like peak centered at omega equals 0, and then a broader peak centered at omega roughly equals to 6, which is the interaction strength U. So this broader peak is likely related to transitions between the Hubbard bands, given its energy scale. And we can, just by looking already at these optical conductivity curves, we can delineate two temperature regimes. The low temperature, roughly of order hopping, the Hubbard peak and the Drude peak. So if we look at these dashed lines and the first solid red lines, they scale together with temperature as you increase, as you decrease temperature. If you decrease temperature further, and you get into this the regime where you have these blue lines, you see that the Hubbard peak doesn't change too much, whereas this Strudel-like peak is becoming narrower and it's becoming taller. In other words, the conductivity is increasing and the resistivity is decreasing as you decrease temperature. Okay, before I go on, so that you can understand exactly what I mean by the error bars in the next slide, let me quickly discuss sources of uncertainty in these calculations. So first, there is always the possibility of finite size effects since we're doing a calculation on a finite size cluster. We can check by comparing against larger clusters, which are more expensive, so we restrict the parameters that we check. So here, I showed six curves here from 4 different simulations for various 8x8 clusters, 12x8, 12x12, and 16x8. And again, this is the optical conductivity obtained by analytic continuation versus frequency. You can see that the curves more or less lie on top of each other. The value at DC is within a few percent of each other for these different cluster sizes. And this is at a temperature of equal to 1 and 1/3. So from this, we can be fairly confident that we are not being significantly affected by finite size effects for the parameter regime of our simulations. There is also always stochastic random error from Monte Carlo sampling. We estimate this via bootstrap resampling. So we can take a subset, or we can resample the set of all of the Monte Carlo Markov chains, and then perform the same procedure and see how much spread there is in the final result. So these are examples of that procedure. This is just a dump of data showing, giving you an indication of roughly how much spread there is due to random error. So you can see that at higher temperatures and down to around beta equals 4 or so, the different bootstrap resamples are pretty much agreeing with each other. I think there should be 1,000 lines here, and you can see maybe 2 or 3 that are kind of visibly separated from the rest. As you go to a lower temperature regime of closer to our minimum temperature where the sign problem becomes rather severe, now you can see that there are more spread. So the error bars that I'm plotting on the next slide are related to this amount of uncertainty. Finally, there is, of course, the issue that no analytic continuation procedure is perfect. There is going to be systematic error, which we cannot quantify exactly, otherwise we could just subtract it out, but we can try to estimate and see what it does. So in the next slide, what I'm going to be showing is sort of a mock data numerical experiment to test the analytic continuation. So the procedure, which I just wrote out in text, is this. So first, we propose various exact spectra, such as Lorentzians of various varying widths, maybe plus a peak at higher energy. We transform that to imaginary time, and then we add the same noise that was in the Monte Carlo calculations to this exact data in imaginary time. So now we have a mock set of data to perform analysis on. We run the same code for analytic continuation on this exact data plus Monte Carlo noise. And then we go all the way back and compare the reconstructed spectra to the exact spectra that we started with. So on the left here, I plotted the half width, half maximum versus in units of temperature for the exact spectra versus the reconstructed spectra after doing maximum entropy. So you can see that, and these are adding noise from various different temperatures. You can see that the stats line is the ideal result where the width of the peak does not change at all after this reconstruction procedure. And you can see that that's roughly satisfied if you start out with an exact spectra that is broader than roughly 2 or 3 times temperature. What I plotted here is similarly, if we just look at the result of the reconstruction, the half width, half maximum of the maximum entropy result. This is the ratio of the DC conductivity to the exact DC conductivity. And you can see that as long as the reconstructed half width, half maximum is something around 2.5 times greater than temperature, the reconstructed result is within around 10% of the exact result. So if we assume that these are reasonable exact spectra to start with, to gauge the accuracy of our analytic continuation, then we would trust our data for DC resistivity to within around 10% if this criteria is satisfied, that the final spectra's half width, half maximum is greater than 2 or 3 times temperature. Of course, we cannot rule out the possibility that there is, say, some emergent energy scale at very low temperatures, and that the low energy structure is actually the sum of 2 peaks. But if we assume a single peak, then this analysis would be valid. Okay, so these are plots of the same data, but in the DC limit and taking the inverse to get the DC resistivity. So this is DC resistivity in units of h bar over E squared versus temperature. Here we can see that there are 2 temperature regimes. One is a high temperature regime, which looks rather doping independent and linear in temperature. And the other regime is a low temperature regime. These are separated at around a temperature of 1.5 times the Hawking. In the low temperature regime, you get insulating behavior at half filling, and then when you dope it, you can see quite a bit of temperature dependence, and we'll look at this in more detail in a second. Let me first talk about the high temperature limit, which was already mentioned in the previous talks. For any model with a limited bandwidth and limited energy scales, we expect that you have linear resistivity from in the infinite temperature limit. You can see this by looking at formula like these. For instance, this is the optical conductivity, and the temperature dependence comes from the temperature dependence of the current correlation function, and from this prefactor. And this prefactor just becomes a factor of beta in the infinite temperature limit. And the current correlation function, we would expect that to go to some fixed form as you go to infinite temperature. So your conductivity just becomes simply a function of 1 over T. In other words, T times your conductivity is constant. So your resistivity should scale as T. Now let's look at low temperature. This is what happens if we just zoom in. This is the same data just zoomed in into a smaller section here. And you can see that at low temperatures, you have more doping dependence, but things still look remarkably linear. So this is going from 5% doping here to 30% whole doping here. And also the resistivity is still rather large in natural units of h bar over E squared. So these are signatures of strange metallic behavior down to temperatures of 0.2 times Hawking, which is the lowest that we can access due to the sign problem. So it's based on the Monte Carlo calculations, we cannot really say what's going on at lower temperature, whether there is a crossover to the Fermi liquid regime or whether linear resistivity might continue, possibly with a different slope. There's one way to analyze this data is if we assume diffusive transport, is to use the Nernst-Einstein relation, which relates the conductivity to the compressibility times the diffusivity. If I invert that equation, what you get is that the resistivity rho here is equal to the inverse compressibility times the inverse diffusivity. What we see is that these two temperature regimes that I discussed in the previous slides, in the low temperature regime, the compressibility is sort of approaching its 0 temperature value. And it's not too temperature dependent, whereas the diffusivity is becoming more temperature dependent here. Whereas at high temperatures, the compressibility is the thing that dominates. The compressibility is very temperature dependent, and it's approaching its infinite temperature 1 over T limit, or in other words, the inverse compressibility is approaching something that scales with T, whereas the diffusion constant is approaching some limiting plateau value. Now, if we look at the doping dependence here, you can see that on first glance, there's a lot of similar behavior in the resistivity and in the compressibility. And when you divide out those two to get the diffusivity, some of that cancels out. So it seems that a lot of the doping dependence of the resistivity derives from the compressibility, even at low temperatures. One final comment I want to make is that sometimes it's, so if we look at these plots, it seems that we are going through an energy scale of bandwidth, which is HT here, and an energy scale of U equals 6, the interaction strength, without too much happening, it seems. But when we're working with parameter regimes that are intermediate, it's a more nuanced question. So in this slide, what I'm showing is the compressibility of the Hubbard model in the atomic limit. So in this model, there is only one energy scale, the interaction strength U. This is the inverse compressibility plotted versus the temperature in units of interaction strength. And here also, if you just look at temperature equal to U, it seems like not much is going on. Basically what's going on is that this is a matter of factors of order 1. There is a crossover in this Hubbard model in the atomic limit, but it happens at temperatures of order U over 4. So you can see that also in this inverse compressibility, there's a regime where doping dependence sets in, and a regime where things are more or less doping independent, separated roughly at temperature U over 4. In the Monte Carlo data, what I showed in the previous slides, this crossover is happening at something on the order of 1.5 times the Hawking, which happens to be also equal to U over 4. So it's quite difficult to say whether this crossover temperature is related to U or if it's related to the bandwidth or the Fermi energy. Whenever we're looking at data from a single parameter, for a single set of interaction strength, it's really difficult to disentangle these energy scales. So we cannot simply judge that there is nothing going on as we cross over an energy scale of U. Okay, so to quickly summarize, before I move on to the second part of my talk, we see strange metallic transport over a wide range of doping and in 2 temperature regimes that are separated roughly at order hopping. In a high temperature regime, things are doping independent, and the temperature dependence of the resistivity derives from the compressibility. In the low temperature regime, we get significant doping dependence, but large T-linear resistivity for all metallic cases. And the diffusion constant is what controls the temperature dependence. Okay, now to move on to the second part of my talk, I want to discuss the Hall coefficient. This is work that is in this preprint on the archive here, done primarily by Huang, who is a student in Tom's group. So first, the Hall coefficient, we know that for non-interacting and weakly interacting systems, it's completely determined by band structure considerations and perhaps the angular dependence of the relaxation rate. And it tells us about effective carrier densities and about Fermi surface topology. The question we want to address is what happens in strongly interacting systems? What does the Hall coefficient still tell us? Does our intuition from weak coupling theory still apply here, even if we're in a regime that is that probably doesn't have quasi-particles? And also another question is, how can we even calculate the Hall coefficient? The first part of my talk was simply about sigma xx, and we saw how many manipulations we had during this analytic continuation procedure we had to do to get this. Here we're looking at a combination of 2 things. So what do we do? Well, the first idea you might have is that you can just add on a small magnetic field to the simulation. You get some phase factors on the hoppings, and then you calculate sigma xy by some analytic continuation procedure again, and then divide out the magnetic field. That's one possibility. Another possibility is that you can directly calculate a 3-current correlation function, shown here, with Jx, Jy, Jx, and analytically continue to omega. Finally, there is some tricks by Asa Auerbach, who wrote down this formula for the Hall coefficient. And it's quite amazing. It's described in detail in these 2 papers. The formula is that the DC Hall coefficient is a sum of a bunch of terms and an infinite series of terms. This is the 0th order term, which will be what I'm showing in the next few slides. And these are operator inner products, which are simply thermodynamic susceptibilities. So no analytic continuation is needed to apply this formula, and it's quite amazing because this is a formula for a quantity on the left-hand side that is the ratio of two dissipative response functions, whereas on the right-hand side you have simply a sum of susceptibilities in some particular ratio. Here, this M is the magnetization operator, and J are the current operators as before. So we simply need to evaluate these thermodynamic susceptibilities in order to calculate these coefficients. Okay, so let me show you the data now. This is from DQMC on an 8x8 cluster with T prime set to 0 to simplify the calculations because the magnetization has terms whenever you have a non-zero T prime. We see that for weak interactions, a small hole doping, we know that small hole doping leads to an electron-like Fermi surface, and hence you get a negative Hall resistivity here. Now, what we're finding is that as you increase your interaction strength, at some point for small dopings, the Hall coefficient suddenly becomes, sorry, not suddenly, the Hall coefficient becomes positive instead of negative. So what's going on here? Why is there a change in the sign? Well, we know that in weak coupling theory, the sign of the Hall coefficient relates to Fermi surface topology. So let's try to study that from the same Monte Carlo data. So now let's look at single particle properties. Now to be 100% clear, on a finite size system at finite temperature, we cannot truly define a Fermi surface, which should be defined as a discontinuity in the momentum resolved occupation. But here we have a discrete grid, and we're at finite temperature, so we do not expect a sharp discontinuity in N of K. But we can take an operational definition for the Fermi surface, which is we look at the low energy spectral weight, which can be calculated this way as the single particle Green's function at beta over 2, which relates to the spectral function through this integral equation. And this is simply a factor that is peaked at low frequencies of order temperature. And if we make a 2D plot of that versus momentum, you can see where there is spectral weight at low energy. So for instance, at U equals 4 times T, this is the Brillouin zone, and these are the momenta, and the color represents this quantity beta times G at K at beta, imaginary time beta over 2. These blue crosses indicate where we have a local maxima in the spectral weight. The specific definition that we take is that at each blue cross is higher in intensity than 6 of its neighbors. This pink dashed line is the non-interacting limit. You can see that for 10% Ho doping, for weak interactions, the operational Fermi surface defined by these blue crosses match very well with the non-interacting Fermi surface. As you increase the interaction strength, you can see that this electron-like Fermi surface becomes hole-like. So what happens is that these strong interactions can change the Fermi surface topology from electron-like to hole-like. Now, here in these white dashed line, what I plotted is the Hubbard 1 approximation. So this change of Fermi surface topology due to strong interactions is something that's fairly well known. It's been studied in many papers, such as the ones that I listed here, and also discussed in one of the previous talks from this conference. Now, if we try to put things together, what we see is that in Hall coefficient, strong correlations can push the sign from being electron-like, negative, to positive. And we see the same thing happening in the single particle spectra. So what we conclude is that even in the presence of strong interactions where we might not think there are any quasi-particles present, there is still a connection between the sign of the Hall coefficient and the topology of the apparent Fermi surface, defined by the locus of maxima and the low energy spectral function. Okay, I think I am close to the end of my allotted time. So let me just quickly summarize. In the longitudinal transport, we see large T-linear strange metallic transport and a crossover from a doping independent high temperature regime to a more doping dependent low temperature regime. For from looking at the Hall coefficient, we see some correspondence between the Hall coefficient sign and Fermi surface topology, even though we are at very strong interaction strengths. That's all. Thank you.
Okay, are there any questions? And then I'll just go to the microphone.
So when U is equal to 16 and you have a positive Hall coefficient, the Hall number that you would extract, how different is it from just doping?
It is, so let's see, let me first answer this directly. It is very different. So you can see here, you can see here that for 5% doping, 10% doping, it's not too dependent on doping. But this is more subtle because here we're considering a tight binding. We're considering a tight binding type of Hamiltonian rather than something that's like k squared over 2m. So because of the angular dependence of the Fermi surface, in general, we do not have there is not a too crisp of a connection between the actual carrier density and the value of the Hall coefficient. For instance, if we go to weak coupling, you can see that the Hall coefficient, which should be 1 over the carrier density, is actually 0 at half filling, and that's simply because of particle symmetry. And for small doping, then it goes linearly from there, even though the carrier density is changing only a little bit.
Okay, so I guess Antoine has a question.
Antoine, would you like to go ahead?
Yes. Well, thank you, Edwin. Obviously, these quantum Monte Carlo calculations are real tour de force. I have a question more on the first part of your talk when you described the optical conductivity and the temperature dependence of the resistivity. So how do your results compare to previous results using other techniques like DMFT or high temperature expansions or FTLM in terms of both temperature dependence and transfers of spectral wave as temperature is changed?
Right, let me go there. So I think, as far as quantitative comparisons go, we're unfortunately using a different parameter set because this is these simulations were started before we were aware of these other more recent results from finite temperature Lancelot's method, and due to the limitations of the quantum Monte Carlo method for larger values of U. But qualitatively, we see many similarities, such as the scaling of the optical conductivity and temperature in the high temperature regime. And we cannot go to low temperatures to compare carefully against DMFT, where you've seen a Fermi liquid regime with a more quasi-particle based picture is applicable.
But it looks to me like the whole structure of the transfers of spectral wave that you are getting are very, very similar to what was obtained with DMFT, right? Which is perhaps not so surprising because the temperature range is relatively high.
Right. Yes, I agree. These qualitative transfers of spectral weight that we see in this temperature dependence are quite similar to what has been seen before by DMFT.
Okay, thank you.
Okay, there's one more question from Manuel. At high interaction, there are also two sign changes with temperature in the Hall coefficient. Is it known where this is coming from?
Right, yeah, that's a very good point. So we see that there is significant temperature dependence and there's two sign changes. I can comment on one of them, which is at high temperatures, these dashed lines here are taken from the semi-classical limit. So what we're seeing is that as you, for these high interaction strengths, as you increase the temperature significantly, you're approaching some semi-classical limit. For what's happening at lower temperatures, that we are not as sure about, but this is still an ongoing topic of investigation.
Okay.
Thank you.
So let's thank the speaker.